Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. While twisted pair cabling dominates modern office environments, and fiber continues to expand across long-distance and high-speed infrastructures, there are still several other physical media types that play crucial roles in networking. Among them are coaxial and twinaxial cables. Though they are used in more specialized applications, understanding these cables is important for both historical context and current data center or service provider use. These media types support everything from cable modem internet access to ultra-high-speed interconnects in data centers, and their presence in certain environments makes them relevant to Network Plus certification and real-world deployment. The Network Plus exam includes both coaxial and twinaxial cables under its physical layer objectives. You might see them referenced in scenario-based questions or in cable matching diagrams. Recognizing when and why to use coax or twinax, understanding the connectors involved, and knowing the key technical characteristics will help you differentiate these from twisted pair or fiber cables. These questions often focus on use cases, signal behavior, and performance constraints, particularly in legacy environments or specialized segments, such as telecom and high-density server racks. Let's begin with coaxial cable. A coaxial cable features a central conductor made of copper or copper-clad steel, which carries the signal. This conductor is surrounded by an insulating dielectric layer that keeps the signal isolated from the next layer, a metal shield or braided wire that blocks external electromagnetic interference. The entire assembly is then wrapped in a protective outer jacket. This layered structure allows coax to carry signals over longer distances with better shielding than twisted pair, making it useful in certain physical environments or for specific applications like cable TV or broadband internet. Coaxial cables transmit signals using electromagnetic fields. The shielding around the central conductor minimizes signal loss and provides a strong barrier against external interference. Because of its construction, coaxial cable can maintain signal integrity over longer distances than unshielded twisted pair. This makes it well suited for scenarios where shielding is essential, such as in broadcast environments or across large buildings where maintaining signal strength is critical. Two common types of coaxial cable used in networking and telecom are RG6 and RG59. RG6 is used primarily for broadband internet, satellite connections, and digital cable TV. It has a thicker core and better shielding than RG59, which allows for higher frequencies and longer cable runs. RG59, by contrast, is more flexible and was traditionally used for analog video systems and older CCTV installations. The difference in shielding diameter and supported frequencies means that using the wrong type can affect signal quality and compatibility with certain equipment. Coaxial cables are most commonly terminated with F-type connectors, especially in consumer broadband and television services. F-type connectors are threaded, creating a secure connection that resists loosening due to movement or vibration. These connectors are used with RG series coaxial cable and are standard in home internet installations, where an internet service provider delivers a coax connection to a cable modem, which then converts the signal into Ethernet for the customer's network. In the early days of Ethernet, coaxial cabling was a common standard. Technologies like 10-base-2 and 10-base-5 used coax to connect computers on a shared bus. These networks required terminators at each end to prevent signal reflections, and tapping into the cable required T-connectors or vampire taps. While innovative for the time, coax Ethernet was eventually phased out due to its complexity, limited scalability, and the advent of easier-to-use twisted pair solutions like 10-base-T. Despite being mostly retired in Ethernet applications, coax is still very much alive in broadband internet. Cable modems provided by internet service providers receive the service via coaxial cable, usually RG6. Inside the modem, this analog or digital signal is demodulated and handed off via a standard RG45 Ethernet port, allowing for connection to a router or switch. This setup is still common in residential and small business installations and represents one of the last mass market uses of coaxial cabling in networking. Twinaxial cable or twinax differs significantly from coax in structure and function. Instead of a single central conductor, twinax contains two conductors within a shared shield. These two conductors carry differential signals, meaning the voltage difference between the wires carries the information, not a reference to ground. This balanced signal method provides excellent noise immunity and allows for extremely high-speed transmission over short distances. Twinax is primarily used in data centers, particularly for high-speed interconnects between switches, servers, and storage devices. Applications of twin-axial cabling include direct attach copper, or DAC, cables. These are factory-terminated twinax cables with transceivers on each end, typically used for 10 gigabit or higher connections within server racks. DAC cables are used to directly connect network interfaces to switches without the need for optical transceivers or fiber cabling. Because they are inexpensive, low power, and very low latency, DAC cables are ideal for top-of-rack switching and dense interconnects where cable length does not exceed a few meters. The connectors used with twin-axial cabling are often part of the SFP+ or QSFP+ direct attach interface family. These connectors are hot swappable and designed to fit into switch or server ports just like a fiber transceiver. DAC cables can be passive, where the signal requires no additional boosting, or active, where integrated electronics help maintain signal integrity over slightly longer run. Because DAC cables are fixed in length and factory tested, they offer predictable performance and are well suited for high-speed environments. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Understanding how coaxial and twinaxial cables compare to other common media types like twisted pair is essential. Coaxial cables offer superior shielding and resistance to electromagnetic interference compared to unshielded twisted pair UTP. This makes them more suitable in environments where external noise could disrupt data transmission, such as industrial areas or alongside power cables. However, twisted pair cabling is more flexible, easier to install in tight spaces, and less bulky overall. Twisted pair also supports Ethernet switching over structured cabling systems, making it more practical in most enterprise and residential networks. Twinaxial cabling has its own set of physical characteristics that define its use. Twinax is significantly stiffer than either coaxial or twisted pair cabling. This rigidity makes it less suited for installations that require cable bends, routing through tight conduits, or frequent movement. Because of its design and shielding, it also tends to be heavier and thicker than twisted pair cables. Twinax cables are also typically pre-terminated and cut to specific lengths, meaning they are not field customizable like Ethernet cables that can be crimped on site. These factors restrict twinax usage to specialized, controlled environments such as server racks. When it comes to performance, twinaxial cables are capable of supporting extremely high-speed connections. Most direct attach copper DAC twinax cables support speeds of 10 gigabits per second, and many support 25, 40, or even 100 gigabits per second, depending on the cable and transceiver type. This makes twinax the go-to choice for ultra-low latency, high-bandwidth connections between switches and servers that are located in close physical proximity. In contrast, coaxial cable is typically limited to lower-speed applications, such as analog video, RF transmission, and broadband cable internet, and it is not used for high-speed LAN connectivity today. Deployment scenarios for these media types vary significantly. Coaxial cable is most commonly found in residential environments, where internet service providers use it to deliver broadband to homes. It is also still widely used in television distribution networks. In contrast, twinax is found almost exclusively in data centers and high-performance computing clusters. It is ideal for connecting top-of-rack switches to network interface cards in servers, or for linking switches together in high-speed, short-distance applications. These environments often require high bandwidth, low latency, and predictable performance, which twinax is well-suited to deliver. Interference resistance is one of the key benefits of both coaxial and twinaxial cabling. Coaxial cable achieves this with its thick outer shield and grounded design, which helps block external noise from degrading the signal. Twinaxial cable uses a combination of shielding and balanced differential signaling, which cancels out common mode interference. In this method, signals are sent in opposite phases along the two conductors, and any interference picked up along the way is eliminated during signal processing. Both of these methods offer superior interference resistance compared to unshielded twisted pair, especially over short to medium distances. Despite its shielding advantages, coaxial cabling does come with limitations. It is bulkier and harder to work with than twisted pair or fiber, especially in large installations. Its stiffness and thickness can make routing difficult in tight spaces, and it is not ideal for cable-dense areas like structured wiring closets. Coaxial cable is also not scalable for modern Ethernet applications beyond the cable modem use case. While it supports internet access at consumer speeds, it does not deliver the bandwidth, flexibility, or switching capabilities required for modern enterprise or cloud environments. Compatibility considerations are especially important with both coaxial and twinaxial cables. Coaxial cables require the correct connectors to function properly. Using mismatched or poorly installed FTU connectors can lead to signal degradation, reflections, or total loss of connectivity. Adapters may exist for converting between coax and other cable types, but they can introduce signal loss or fail to support the required frequency range. Twinaxial cables are even more sensitive than on skis. Because they are typically factory terminated and intended for specific devices, improper mating with incompatible ports can damage equipment or result in non-functioning links. When preparing for the Network Plus exam, expect questions about coaxial and twinaxial media to focus on recognition and use cases. You might be shown an image of an FTUP connector and asked to identify what cable it is used with. You may see a question about which cable type is appropriate for a server to slip 10 gigabit connection and need to know that Twinax is the correct answer. Other questions may ask you to match cable types to characteristics, such as shielding level, speed capacity, or typical application environment. Being able to distinguish these media from twisted pair or fiber is a core part of physical layer understanding. In summary, coaxial and twinaxial cables serve specialized but important roles in networking. Coaxial cabling is still a vital part of broadband delivery, television systems, and legacy Ethernet setups. Twinaxial cabling, though more niche, plays a critical role in high-speed data center networking, offering powerful performance in short-range, low-latency links. Both cable types offer strong interference resistance and specific physical characteristics that make them well-suited to their environments. Knowing when and why to use them is essential for designing, supporting, and troubleshooting modern networks, and for passing the Network Plus exam. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.